Okay, so I created two previous videos where we started with a system diagram and we found the system functional and the impulse response. Now we have four more things here, and these are all quite simple. I'll do all of these in a single video. So I'll take this down to the bottom and we'll continue with our example. Okay. Right. So first of all, find the z-transform. Well, we're done. Basically, you just take r and replace it with 1 over z. Right? So here we have our response function, and I just replaced the r with 1 over z. Now it's actually more convenient to use the form up here. I'll use this form here. Oops, it doesn't grab. Let me grab this way. So and take it down. So let's go. Well, this will go to r goes to 1 over z. 1 over z plus 1 minus 1/2 plus b bar over 1 over z minus alpha plus b over 1 over z minus alpha bar. And it would be good to rearrange these terms here so that the form is like z minus something or z minus something if you're from South Africa where I am now. So if I want to rearrange these denominators so I have z minus something, I would have to multiply by z over alpha or z over alpha or minus z over alpha to get rid of this minus alpha. Right? Because if I want a z in the denominator instead of a 1 over z, I'm going to have to, the z will go over in the second term. So to get rid of the minus alpha, I'm going to have to do minus z over alpha. So let me just indicate that in another color, what I'm doing. I'm going to multiply top and bottom by minus z over alpha. Okay. And this one here would be minus z over alpha bar. Sorry, minus z over alpha bar. There's a lot of multiplying on the top and on the bottom. Okay. All right, so if I do that, I'll go back to my purple color. I have 1 over z minus 1/2. And then looks like I'm going to have a minus again, minus times z over, and then I'm multiplying both terms on the bottom, so this becomes, I'm going to write the second term first. It's going to be z minus 1 over alpha. And notice the 1 over alpha here. And then I have minus b over alpha bar times z bar over z minus 1 over alpha bar. And you notice that these roots here are exactly the powers here that are showing up. All right, so that's interesting. Okay, so we're good with the z-transform. We have the z-transform. Let's see, am I connected? There we go. So this is the z-transform. And again, it's perfectly fine to write these in terms of constants as long as my constants are defined. All right, so b and alpha are defined above. Okay. And I think in some ways it's even preferable. Okay, all right. Now, find the poles and the region of convergence. So the poles here are your 1 over alpha and 1 over alpha bar. And there's also a pole at 0. Okay, those are the poles. Okay, and then I want to find the region of convergence. Well, when I did the series here, notice how I did the series here. The series terms, I had 1 over 1 minus r over alpha. Okay, and this r becomes a 1 over z. So this only converges if this term has absolute value less than or equal to 1. Okay, so the series converges when 1 over, when r over alpha, and if I have alpha conjugate, it has the same absolute value as alpha, so it only converges when this is less than 1. Now that's the same thing as saying 1 over z alpha is less than 1. And you can rearrange that to say that z has to be greater than 1 over alpha, right? The larger z is, the better this converges. So you need z to be bigger than 1 over alpha. Okay. So these terms converge when z is bigger than 1 over alpha. Now this one does. This just has and this should be absolute value z. Sorry. This one here we don't have to worry about. This is just this one is for z greater than 0. So everything will converge if z is greater than 1 over alpha. And both of these two have the same region of convergence, right? This is greater than 1 over alpha bar. It's the same. It's the same thing. Okay. Right. So you need to check the radius of convergence for all the terms. But the way you get the radius of convergence is you look at how you expand it with a 1 minus, and make sure that the expansion term has absolute value less than 1. Right? So that's the radius of convergence, or region of convergence, whatever you want to say. Okay, so the next item on the list was to write the impulse response as a sum of discrete exponentials. And we can go up here and do that. Let's grab the impulse response. That was this here, right, my impulse response. And really I just want to break it up so it looks more nicely. You can see that there seem to be common patterns for the different values of n. Right, so let's paste it here. So really, you can see that they're kind of three parts. Well, two parts. There's this part here that doesn't depend on beta bar and beta. There's this part that depends on beta bar. There's this part that depends on beta. All right. So I'm going to break that up into 3 parts. So I'm going to write, so I just write it this way. I'll write h of n Well, let me separate off these two parts here, this minus 1/2 and this 1. Okay, so the minus 1/2 only occurs when n equals 0. So I can write this as minus 1/2 delta of 0. And this 1 only occurs when n equals 1. Right? So I can write this as plus 1 times delta of 1. Now let me simply generalize the next term as plus beta bar over alpha times, it looks like it's times alpha, 1 over alpha to the n. And then I have beta over alpha bar, 1 over alpha bar. Now I will point out that these terms here, I would write them this way, but these terms here really are exponential terms. So just note, this is the same thing as this 1 over alpha to the n. It's just the same thing as e to the log, I'll use natural log, 1 over alpha times n. Right. So really this is like an exponential term. And if you have imaginary number here, you get imaginary stuff here. We get negative numbers and stuff. But this is the connection between discrete and continuous. With continuous, you do have this exponential. But with discrete, we simply write it this way. Okay, last item on the list is find the system response to simple signals. So now that's what we want to do now. Okay, and this here was simply write the system response, write the impulse response as a sum of exponentials, because you can always do it this way. All right, now let's find the system response to some simple signals. Let me give some example. I'll give you an example of an x. That's a signal. So let's do an example of x. And my x will look something like this. This is actually what's called the second derivative signal. I'll put this is my n. This is 1, 0, minus 1. And then here I'll have a 1. Here I'll have a minus 2. And here I'll have a 1. So this height is 1, this height is minus 2, this height is 1. Now, for me, I think the best way, so this is x of n. Now, you can write out x of n, but for me, the best way to represent this is using the R notation, because it really tells me what's going on with this signal. So I can write this signal x in the R notation. It's equal to minus 1, and then this is R inverse, right? Because R is 1 delay, so I'll call it minus 1 R inverse. This minus 2, and this plus, and then this one here is going to be plus R. I'm sorry, it's not minus 1 R inverse. It's 1 times R inverse, sorry. The R inverse refers to the minus 1, right? And then this is plus R. Now, let's also write h of n. And I'll write it in the same way. All right, so let me go up here. There's my h. And I've got, let's do this. All right, so this here is minus 1/2 delta of 0, so there's no delay. Then this one has a delay of 1, so this is going to be R. Then this one here is going to have delays associated with the different values of n. So, and I'm going to write the sum over m just to distinguish from n. And what this means is that the nth term is going to be R over alpha to the n. And then I have the same with the complex conjugate. With the alpha bar. Okay. So to get the response, I just need to multiply these two polynomials. So to get the response of the system to x of n, I simply multiply these two polynomials. Okay? Right now, it gets a little bit complicated, but let's just do, for example, suppose I wanted to get the response at time 3. Okay. What I can do is I can consider the contribution of each term in x to the signal at time n equal 3. Okay. First of all, we have the R inverse term. Now, what's the R inverse term going to do? Well, it's actually going to affect the H terms with R equals 4 and pull them back and produce a coefficient and produce a so this is the R cubed term. So I multiply R inverse by R to the 4th term, then I will get an R cubed term. So this is going to give me the sum of R to the 4th terms in H of n. Okay? Then I have the minus 2. And this gives me the sum of R cubed terms, but times minus 2. Okay? And the R is going to give me, okay, the sum of R squared terms in Hn. Okay? So in order to get the n equals 3 response, I can do it I can break it down that way. I can see what x does, because I can think of this as 3 impulses. The 3 impulses produce 3 responses that I add up together. Okay? So the n equal 3 response, the response at time 3, so I'll get from the R inverse, I'm going to have to look for the R cubed terms. The R to the 4th terms, right? What are the R to the 4th terms in H of n? So this is going to be R to the 4th terms. Okay. Well, that's just with m equal 4 here, right? There should be a m, sorry. There should be a m as well. Okay. All right. So with R to the 4th, I have R to the 4th over alpha to the 4th. And I have the minus beta bar over alpha, and then I can just write that as 1 over alpha to the 4th, because I'm going to factor out the R to the 4th. I mean, the R to the 4th is going to multiply the R inverse and give me a minus 3. Okay. So I have that term, and I also have the R to the 4th term from here. Okay. And that's going to give me minus beta over alpha bar, a 1 over alpha bar to the 4th. Okay. All right, so I have 3 contributions. That's the first one. Then I need to have I need to find the R cubed terms in here, and I'm going to multiply those by minus 2. Okay, so I'm going to have plus minus 2, or I'll just say minus 2 times, and then these are going to be the R cubed terms. So what about the R cubed terms? Well, I don't have any terms down here. There aren't any here. There aren't any here. There's going to be an R cubed term here. So I'm going to have minus beta bar over alpha, and then this is just going to be 1 over alpha cubed, and then this is going to be minus beta over alpha bar, and then this is going to be 1 over alpha bar cubed. Okay. And then finally I'll get the terms from R squared. And that's going to give me quite similar. It's just going to give me minus beta bar over alpha. And then this is going to be 1 over alpha squared. And I'll get minus beta over alpha bar. And this is 1 over alpha bar squared. Okay. So the total result, I can group by minus beta bar over alpha, because that's going to be 1. And then I'll also have a minus beta over alpha, that's going to be 1. And you can see what it is. The first term is going to be 1 over alpha to the 4th. Second term is going to be minus 2 over alpha cubed. And then the last term is going to be plus 1 over alpha squared. Okay. Then I'm going to have a minus b over alpha bar. And then this becomes 1 over alpha bar to the fourth minus 2 over alpha bar cubed and plus 1 over alpha bar squared. All right. So this is for n equals 3. All right. Now, if I was going, in fact, you can see the pattern here. If I was going to do n greater than 3, right, you can see that what's going on here is that this beta bar over alpha, this is going to be 1 over alpha to the n plus 1 minus 2 over alpha to the n, and then plus 1 over alpha to the n minus 1. Okay? And this is going to be minus b over alpha bar, and then I have 1 over alpha bar to the n plus 1 minus 2 over alpha bar to the n plus 1 over alpha bar to the n minus 1. Right. Now when n gets small, it gets more complicated because these other terms come in. These constant terms come in. But they're not going to come in past r squared, you see, because here you have r times r, that's r squared. That's the maximum delay from any signal due to this portion here. Okay, but after that, we get a fairly simple response. And you can see it still has a 1 over alpha and a 1 over alpha bar dependence. So in fact, probably better to write it this way. I could write it minus beta over alpha, and then I could write this as 1 over alpha minus 2 plus alpha times 1 over alpha to the n minus beta over alpha bar. And this is a beta bar. And this is going to be 1 over alpha bar minus 2 plus alpha bar. So you can see times 1 over alpha bar to the n. So you can see what's only happened here is we've introduced this factor when previously we just had the, if you look at the impulse response previously, right, we just had this term here, these two terms here. Okay, so we've simply introduced these additional factors. Okay, so that's actually true for n greater than or equal to 3. Okay, so we've seen how to find the response of the system to some simple signals, and it does. You certainly have to organize your computations. And I think we can stop here. Thanks for watching.